Welcome to the course on biostatistics and design of experiments. We will look at full factorial design. In the previous class I talked about what is the factor and what is the level. So, let us look at for example, the this particular number tells you the level and the exponent tells you the number of factors. Suppose you have 2 raised to the power 1, that is only one factor. Okay. You will have 2 experiments here, one at low, one at high, right. Okay. So, one at low and one at high. The factor A will be done with low level and with high level. Okay. So, you will have 2 experiments done. Suppose we have 2 factors like A and B, okay, at 2 levels, 2 factors, 2 raised to the power 2, that is 4 experiments. Okay. So, we need to do 4 experiments, run 1, 2, 3, 4, and this is one way of representing them. Factor A, when you put minus 1, that is at low level, when you put it at plus 1, you call it high level. So, factor A at low level, factor B at low level, factor A at high level, factor B at low level, factor A at low level, factor B at high level, factor A at high, B at high. So, this is one way of representing. Minus 1, plus 1, minus 1, minus 1, plus 1, plus 1, plus 1. Another way of representing these 4 experiments is like this actually. We call it 1, that is the base level, minus 1, minus 1, and then when you call it small a, that means factor A at a higher level. When you call it factor B, factor B is at higher level. When we call AB, factor A as well as factor B at higher level. Okay. So, this is one way of representing, this is another way of representing. Okay. If you look at only one factor, no, we will call it the 1, that is lower level, and when you say A, small a, that means factor A is at higher level. So, generally we like this one because we can do lot of things with this. Okay. Now, if I want to look at interaction AB, that means temperature pH example I am coming back. So, how do I study interaction AB? All I have to do is multiply these 2 numbers to get this number. Minus 1 into minus 1 is plus 1, plus 1 into minus 1 is minus 1, okay. Minus 1 into plus 1 is minus 1, plus 1 into plus 1 is 1, okay. Do you understand? So, interaction AB is given like this. This is the column for interaction AB, and this is the main factor A and B, this is the interaction AB. So, here you are doing 4 runs and we can get information about the effect of A and the information about effect of B, and we can also get effect of interaction AB. How do we get that? In the previous time I mentioned to you, right, that if I am having a results output, 4 experimental outputs. If you want to look at the effect of A, I add up the results from here divided by 2, subtract it from adding up this and this by 2, because this is at higher level, this is at lower level. If you want to look at effect of B, I add up the results from these 2 experiments, divide by 2, subtract it from these 2 experiment divided by 2, that is average. If I want to look at interaction AB, I will take the results of this experiment, add up, divide by 2, subtract it from the results of this experiment plus this experiment by 2. It is so nice. We can look at the effect of interaction very nicely from this type of factorial experiment. So, that is the beauty of factorial experiment. Okay. And another interesting thing you can see is the number of pluses in this column will be equal to number of minuses. Okay. So, that way you will have a very symmetric. So, 2 pluses, 2 minuses, 2 pluses, 2 minuses. So, there is the type of experiments we do also will be symmetric. That means, we will do in equal number of higher level experiments with equal number of lower level experiments. Even for AB, if you see, you will have 2 pluses, 2 minuses. Okay. Now, let us go to a 3 factor experiment. That means, I am looking at temperature, pH and dissolved oxygen amount on a product yield, for example. So, ABC. So, what will be the design? 2 raised to the power 3, the 2 means 2 level, 3 means 3 parameters. Of course, instead of 2 levels you can also go for 3 levels and so on, we will talk about it later, but most of these factorials experiments we go with the 2 levels. So, 2 raised to the power 3 experiments, that is 2 into 2 into 2 is 8 runs. So, it is like a cube, okay. A will be at low level and high level, B will be at low level and high level, C will be at low level and high level, 8 runs. So, how do we generate the factor experiment? Look, minus 1, minus 1, minus 1, then we put A plus 1, minus 1, minus 1, then for B minus 1, plus 1, minus 1, then AB plus 1, plus 1, minus 1. Now, we keep changing C, minus 1, minus 1, plus 1, plus 1, minus 1, plus 1, minus 1, plus 1, plus 1, then all of them are pluses. This is one representation. If you want to represent the other way, you have 1 A means level A, factor A is in higher level, B means only factor B is in higher level, AB means both factor A and B are in higher level, C means factor C is at high level, AC means factor A and C are at high level, BC means factor factor B and C are at high level, ABC means factor A, B, C all 3 are at high level. So, we have 8 experiments. Look at this, if you look at the column, you will have 4 pluses, 1, 2, 3, 4, you will have 4 minuses. Look at column B, you will have 4 pluses, you will have 4 minuses. Look at column C, you will have 4 pluses, 4 minuses. So, it is very well balanced. This is called a balanced design. Now, how do we get the interactions? A B interaction, you multiply A and B column, okay. Minus into minus is plus, plus into minus is minus, minus into plus is minus, plus into plus is plus, minus into minus is plus, plus into minus is minus, minus into plus is minus, plus into plus is plus. So, AC column A into C, BC is B into C, ABC is all 3 together multiplied. So, minus 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 will give you minus, plus minus minus will give you plus, minus plus minus will give you plus, plus plus minus will give you minus, minus minus plus will give you plus, plus minus plus will give you minus, minus plus plus will give you minus, plus 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 will give you plus. Look at the interaction columns also, so beautiful. You have 4 pluses, you have 4 minuses. So, it is so balanced, okay. So, the factorial designs are always balanced, okay. So, they are called balanced because if you look at the A effect 2 pluses 2 minuses, B effect 2 pluses minus, and they are also called orthogonal because these interactions are also balanced, okay, 2 minuses 2 plus. If you go to the previous slide, look at this BC, it has got 4 pluses 4 minuses, look at AC, it has got 4 pluses 4 minuses. So, balanced and as well as orthogonal. So, factorial designs are always like that, and you have to be very careful when you select it. You should always have a balanced and an orthogonal designs. Please remember that. If you do not have a balanced design, that means if you do not have enough pluses, equal number of pluses and minuses, suppose you prepare a design where you have more pluses than minus, that means you are doing a biased design where you are trying to look at the performance at higher level, okay, which is wrong, because any design should be unbiased. So, you should always have a equal number of pluses and minus, that is one thing. Other thing is your interactions also are balanced, okay. So, that way you can study the interactions also in a equal unbiased manner. So, all these designs, especially the factorial designs are always balanced and orthogonal. So, when you select designs later on, you should always look whether your designs are balanced. If it is not, then you have a bias. That means you are focusing more on one particular level of factor rather than looking at all the levels in a uniform way, okay. So, that is very important when you plan your design. The balance and orthogonality are very, very important when you perform a strategy of design, okay. You can look at interactions, as I said, combination of factors, So, we can look at AB. So, when you develop a regression relation, you will not only have terms like this, we will also have terms like A and B. We looked at it long time back, okay, temperature and pH and so on actually. Okay, so several factors will become significant, sometimes 2 factor interactions may be significant, but 3 factor interactions may not be significant at all, very rare. You will not have a situation where temperature, pH and agitator RPM interacting with each other, but you can have a situation where temperature and pH may be interacting, pH and agitator RPM may be interacting. For example, when I increase agitator RPM, maybe I am dispersing the material better, so the pH is more uniform and so on. So, pH, so 2 factor interactions are generally possible, but 3 factors and 4 factors are very rare. You need to keep that point in mind. It does not happen every day, okay. It does not happen at all in most of the situation. So, main factors will be significant, 2 factor interactions will be significant, okay. So, but there are drawbacks of this full factorial design, like it is 2 raised to the power n, right. So, n is 1 means 2 experiments, 2 means 4 experiments, 3 means 8 experiments, 4 means 2 into 2 into 2 into 2, 4, 16, 5 means 32, like that it keeps on increasing actually, no, it is a huge. Imagine if I am doing a 15 parameters, factors, 2 raised to the power 15, that is a huge number of experiments, no, that will not do at all. So, there is something called fractional factorial design. We will look at fractional factorial design in more detail as we go along, but fractional factorial designs are fractions of this main full factorial design. You can have half fractional factorial, that means you will do half of the full factorial, you can have 1/4 of full factorial, you can even have 1/8 of full factorial. So, you will do much less number of experiments like half, 1/4, 1/8, but you lose out on some other parameter, we will talk about it later on, but the number of experiments go down if you are doing half or 1/4 of the full factorial experiment, okay. Okay. So, this figure tells you as you keep on increasing the factors, it keeps on going up, okay. So, that is not a very good idea to do actually, okay. So, if you do a full factorial, for example, if I take 2 factors like A and B, you are doing 4 experiments. So, you are looking at main effects of A, main effect of B, that is 2 main effects, and we can also study the interaction A B, that is called a second order interaction. Suppose you have 3 factors A, B, C, there are 3 main effects, okay. Then you can have 3 second order interaction A B, A C, A C, and you can also have a third order interaction A B C. If you look at 4 variables or parameters or factors A, B, C, D, you will have main effects A, B, C, D, then you will have 6 two-way interactions like A, B, A, C, A, D, B, C, B, D, C, D, that is 6. You can have 4 three-way interactions A, B, C, A, B, D, B, C, D, A, C, D, and so on, you will have 4, and there will be 1 4-way A, B, C, D, like that it goes, right. So, you in many situations you will end up having very large number of interactions, and as I said, it is very rare to have a 3-way interaction. So, it is very rare, that means this portion is actually useless. We are doing too many experiments, and we are not going to anyway look at 3 level or higher level interactions, higher order interactions, okay. That means we are doing too many experiments. Look at box, he said there tends to be a redundancy in full factorial design, because this is a redundancy, because 3 level or 3-way interactions are very rare, okay. That is why it is always good to do fractional factorial designs to exploit this redundancy. Like I said, fractional factorial, if you do a half fractional factorial, we will be doing half of a full factorial, or if you are doing 1/4 full factorial, that means that could be a 1/4 fractional factorial design, because nobody is interested in 3-way or 4-way or 5-way interaction, that is very rare. So, all these portion is all redundant, so all these experiments are waste, you know. That is why it is better to always do a fractional factorial design. And as you know, it is always everybody likes to do less number of experiments because of time constraint, because of resource constraint, but with less number of experiments we should be able to get as much information, especially the main effects and the main interactions, okay, the two factor interactions AB, AC, AD, BC, BD, these are the things we are interested in. If it is ABCD, we are interested in main effects like A, B, C, D, and then we are interested in AB, AC, AD, BC, BD, CD. We are not interested in ABC, that is very rarely going to happen. So, such is not generally observed in many situations. That is why one goes about doing something called the fractional factorial studies. How do you go about selecting a fractional factorial? Let us look at it in very systematic way. If you go to screening designs, like I said, initially you may select large number of parameters and you perform some experiments. So, in that screening design you are interested to identify which are the critical parameters, which are noise parameters, eliminate the noise, take only the critical and spend more time. So, in screening designs we take large number of factors, we are more interested in only main effect, we are not even interested in interaction. So, in screening design we will perform only few experiments, get the main effects and then take only few important ones and then go and do a detailed design, okay, that is called screening design. So, there are many types of screening designs, one is called the Plackett-Berman design, the other one is called the resolution 3 fractional factorial design. I will talk about what are these actually, these are some screening designs which are used to just screen large number of parameters or factors, eliminate quickly which you think is not necessary by doing minimum experiments and select only those which are very critical and then do a detailed study. That is what screening design is all about actually. We will spend more time on this Plackett-Berman design and resolution 3 design later on. Generally the screening designs involves a lot of fractional factorial designs. Okay, let us look at a simple picture. Imagine I have 3 parameters or factors A, B, C. So, 2 raised to the power 3 design, that means 8 experiments. So, how do I change? Minus 1, minus 1, minus 1. So, each one I am changing to minus 1 to plus 1. So, the last experiment will be plus plus plus. You understand? How do we get AB? This into this, minus minus plus, minus minus plus, minus plus minus, minus plus minus, plus minus minus, plus minus minus, plus plus plus, plus plus plus. So, look at here, you need to always cross check whether the balance is there, number of negatives equal to number of positives, and then orthogonality, the interactions also there are 4 positives, 4 negatives, 4 positives, 4 negatives, like that. Okay, now I want to go into a fractional factorial design. Imagine I want to introduce one more factor. ABC was my say the pH, temperature and carbon, but actually I want to study pH, temperature, carbon and nitrogen. So, 2 power 4 will be 2 into 2 into 2 into 2, 16 experiments. I do not want to do 16 experiments, I want to do only 8 experiments and get lot of data. So, what do? I take this design matrix and do a fractional factorial to involve D also. Okay, now where do I put D here? That is the question. Do you understand? I have 4 factors or parameters A, B, C, D, temperature, pH, carbon, nitrogen. If I have to do a full factorial design, it will become 2 raised to the power 4, that is 16 experiments, but I do not want to do 16 experiments, I want to do only 8 experiments, that is half of 2 raised to the power 4 or 2 raised to the power 4 minus 1. So, one of them I want to make it D. So, generally you take the highest order interaction, that means ABC. As I said before, people generally see these first order interaction, but never second order interaction. So, you call this D. So, your design will be only 8 experiments, 4 factors. A will be like this, A is modified like this, B is modified like this, C is modified like this, and D is modified like this. So, if I have temperature, pH, carbon, nitrogen, 4 factors, instead of doing 16 experiments, I am doing half of 16. So, I will have only 8 experiments. So, I take the design matrix for 8 experiments A, B, C, and then I will put the A into B into C as D. So, I will change D in this fashion. Okay, now the question is, there is a catch. What will happen? You already have certain interactions A, B, A, C, B, C. What will happen to D involved? What will happen to AD? What will happen to BD? What will happen to CD? When you do that, you find AB is same as CD. AB I said minus minus plus, minus minus plus, minus plus minus, minus plus minus, plus into minus minus, plus minus okay, so plus minus minus, plus plus plus, plus plus plus. Now, if you look at CD, minus minus plus, plus plus plus, minus plus minus, plus minus minus, minus plus minus, plus minus minus, minus minus plus, plus plus plus. So, AB looks exactly like CD. Same thing I can show that BD looks exactly like AC. Same thing I can show AD looks exactly like BC, and also A looks exactly like BCD, just like D looks exactly like ABC, A looks exactly like BCD, B looks exactly like ACD, C looks exactly like ABD. Okay? And this design is of course 2 raised to the power 4 minus 1, because I have A, B, C, D as 4 parameters. I am doing only, instead of 16 experiments, 8 experiments. So, I am doing 2 raised to the power 4 minus 1. Okay? So, what has happened here? I am able to do away with, instead of 16 experiments, only 8 experiments, but some of these factors are confounded. New term I am using, some of the factors are confounded. AB will look like CD, AC will look like BD, BC will look like AD. So, I will not be able to differentiate between AB and CD. I will not be able to differentiate AC and BD. I will not be able to differentiate BC and AD. And of course, I will not be able to differentiate D against ABC. So, I will not be able to differentiate A against BCD, B against ACD, C against ABD. Okay? So, these have been confounded. Okay? These 2 level interactions have been confounded, and the principal effects or main effects are confounded with these 3 factor interaction. You understand? So, these 2 factors interactions are confounded with 2 factor interactions, and the main effects or main factors are confounded with these 3 factor interactions. So, some information is lost, but what has happened? I have reduced the number of experiments. Instead of doing 16 experiments, that is 2 raised to the power 4, that is 4 factors A, B, C, D, I have reduced it by half. So, this is called a 2 raised to the power 4 minus 1 design. 2 raised to the power 4 minus 1 is 2 raised to the power 3, which is 8 experiments. But in the bargain, what has happened? Some interactions are confounded. AB interaction is confounded with CD, AC interaction is confounded with BD, BC interaction is confounded with AD. That means, I will not be able to differentiate whether if some change is there, is it because of AD or BC, whether it is because of AC or BD, because of AB or CD. Same thing for the main effects also, they are confounded with 3 factor interaction, and that is not a big problem, because generally we do not observe any 3 factor interacting. So, whatever change we see because of main effect, we are sure that it is because of the main effect only. You understand? So, we have lost some information which is not of very big significance unless there is some problem here. AC, the 2 level interactions are confounded, unless you think there is going to be some important knowledge lost. Otherwise this is a very good sort of a screening design for 4 parameters or 4 factors. Instead of doing 16 experiments, I am doing only 8 experiments, okay. And this is called a 2 raised to the power 4 minus 1 fractional factorial design. So, number of runs is equal to 2 raised to the power k minus q. This 2 is the number of levels, your k is the number of factors, q is 1, then say in the previous case 2 4 minus 1. So, that is a half. Instead of 16 experiments I am doing 8 experiments. If q is 2 indicates quarter, okay. Extra q factors are alleged with higher order, we will talk about it later. So, this is called a 2 k minus q or 2 4 minus 1 design. This is a half fractional factorial design for 4 parameters. So, instead of 16 experiments I am doing only 8 experiments in this particular case. Okay. Now, let us look at 6 factors x1, x2, x3, x4, x5, x6. Okay. Now, imagine first I start with the design matrix for x1, x2, x3, x4, that is 4 parameters. 2 raised to the power 4 is 2 into 2 into 2 into 2, 16 experiments, understand. So, I write down these 16 experiments, these are the 16 experiments I write down, okay. And then I can write down the interactions x1 into x2, x1 into x3, x1 into x4, x2 into x3, x2 into x4, okay, then x3 into x4, then 3 level x1, x2, x3, and like that it goes. Now, I want to introduce 2 more factors x5 and x6, okay. Now, where do I introduce? The problem is I could introduce in different places, right. I could introduce in different places the x5 and x6. So, this if I introduce this x5 and x6, that is 2 raised to the power 6 minus 2, that is a quarter fraction design, right. Instead of 2 into 2 into 2 6 times, 4, 8, 16, 32, 64 experiments, I am doing only 16 experiments, that is a quarter fraction of 64 experiments, 2 raised to the power 6 minus 2 fractional factorial design. Do you understand? So, do I introduce x5 here, that is x5 is equal to x2, x3, x4, and s6 is equal to x1, x2, x3, x4. Then if I multiply x5 by x6, what will happen? That will become x1. This is very dangerous. What it means is the principal effect x1 is confounded with their 2-way interaction x5 and x6. Ideally, we always said that principal effects should have an interaction with more than 2 factors, at least 3 factors or more, then that is a good design. Whereas here it is interacting with 2 factors, that is not a very good design at all. So, what do? We need to look at some other columns, so that the principal effects will have a confounding only with 3 factors. Okay. Okay, now if you look here, x1, x2, x3 put it as x5, and x2, x3, x4 put it as x6, then x5 into x6 will become x1 into x4. Okay. So, there is only a 2 factor interactions, okay. Unlike the previous case where x1 is interacting with the 2 factor, x1 is a principal effect, right, whereas here 2 factors are interacting with 2 factors. So, this design looks good. So, you need to think about how to select the column in which you want to put in your new parameter or new factor or new x or new variable, so that you do not end up a situation like this, okay, where a 2 factors interacting with the principal effect or main factor, whereas 2 factor can interact with 2 factor like this. So, this happens in this type of situation where you can have the new variables and the choice is either out of these 5 how to select 2 of them. Okay, when you selected these 2 they are not good. So, what did you do? You selected these 2. Okay. So, that is how you get your design done actually. So, let us continue more on this fractional factorial design, I introduced the terminology called confounding. So, we have these factors confounding. In some situations we have 3 factors confounding with the principal effect or main factor, which is allowed, but you do not want a main effect or main factor confounding with the 2 factor interaction, but it can confound with 3 factor interaction. Okay. So, x1 can confound with x2 into x3 into x4, but x1 should not confound with x2 x3, but 2 factors can be confounding with each other, okay, like here x5 into x6 can confound with x1 into x4, or in the other situation BC is confounding with AD, BD is confounding with AC, CD is confounding with AB. Okay, in this problem there was no problem, we could put D exactly here, whereas in this problem these 2 factors or 2 parameters could be put in any place because there is a lot of choice here. Do you understand? Okay. And selection of the correct column will depend upon which factors get confounded. Okay. So, we will continue on this concept of fractional factorial designs and confounding in the forthcoming classes. Thank you very much.